Okay, so what I'd like to talk about is the use of Monte Carlo simulation. You could think of Monte Carlo simulation as something in between calculation and simulation, which is a nice reconciliation, but probably that's not completely accurate. I would say that Monte Carlo simulation is a means of calculation. But it's actually quite an advanced means of calculation, being able to deal with quite complicated and detailed situations. So let's have a look, and I think by going through the presentation you will realize where probably Monte Carlo simulation fits. So I have some questions today. I was going to offer money for those who answer the questions, so I've got some coins here, £3 coins. It used to be fivers last year, but I think... So why do we have this arrangement? Traction, okay. Specifically, what are we increasing here? Angle of wrap, excellent. Okay, so you can, it's quite a weird arrangement. I think it's from Brazil. So, I have some co-authors to credit. So Stefan is here. Where's Stefan? Raise your hand, Stefan G, to distinguish him from Stefan K. Where's Stefan K? Okay. Richard. Jens is not with us here, and Maria was a student who worked with Richard. So some of the ideas, she worked on some of these ideas in here. Anyone know what this is? UK shipping forecast. Okay, very good. That's £1 for you.
Thank you, Lutfi.
Okay. So I am serious, actually. So that's a shipping. There is a serious reason for this later on. Okay, so let's have a look. We'll have a look at a sample round trip. It's nice we had these two presentations before, Gina's and Jens. You will see actually how this actually fits in between the two. And you can push it as far as you want towards calculation. You can push it as far as you want towards simulation, although it's not really a simulation. So what are the sources of randomness? We look at the round trip time equation from the 1972 to now. So this is actually a sample of a round trip. What are the sources of randomness in a round trip? Why does one round trip look different from the second round trip?
Flow serve.
Say that again?
Flow serve.
Okay, flow serve, but actually, people, what specifically in people? Specific, I want you to be more specific. Someone's arrival time, yes?
Probability of destination.
Destinations and origins. Okay, so that's £2. You should probably share that with the gentleman from down there. Okay, so what I'm suggesting here is the only two sources of randomness, or the only source of randomness in a round trip or in a lift system, are people in two aspects: origins and destinations, and arrival times. This is a round trip, so we have 9 passengers, third to second, ground to fifth, B to 3, 8 to 6, 7 to G, and so on. And that is what we call in the language of Monte Carlo simulation a trial. That is a trial, a flick of the coin. And if we go through that, you will find that actually that's the detailed journey. So that's a detailed scenario. And if we draw it by hand, then we have a passenger getting in at B, so we have a passenger getting in at top button, okay. So we have one passenger getting in at B, so we have one passenger in the car. 2 passengers getting in at G, so we have 3 passengers in the car. Another passenger getting in, 4 in the car. 1 getting out, 3 left in the car. 1 getting in, 2 getting out, 2 in the car, and so on. We know every single detail about this journey, this trial. And because we know every single detail about this journey, if we compile all of that data, we've got a wealth of data. We know so much rather than just knowing the average. So sources of randomness are passenger origins and destinations. We can model that in Monte Carlo simulation. So we can actually, we know how these origins and destinations work. Arrival time, we haven't got that yet, but that's something you can do in the future. Without this randomness, every round trip will be the same as the one before and the one after. Life will be very boring. But more importantly, what's the problem with that? there'll be no work for lift traffic experts and consultants. Okay, so if we look back to the 1972 equation from Barney and Dos Santos, we have H, we have S, and we have RTT. And in fact, what we're assuming here is H is a constant, is an average. S is an average, and thus RTT is an average. But in reality, in every round trip, T is a random variable, which is the round trip time. H is a random variable, S is a random variable. And really what we're saying in calculation, in simple calculation, is that we're taking the average of H, which gives us capital H. We're taking the average of S, which gives us capital S, and then we come up with an RTT. That's why we lost something in calculation. We're going to try to recover that. We're going to go back to these as random variables. So this is a PDF. So instead of talking about an average now, we talk about something different. We talk a probability density function of a random variable. So the random variable is the maximum number of passengers in the car. There's a very, very small possibility or probability that we only needed 2 in that round trip. But it's more likely that we needed 4, 5, 6, and it was very unlikely, actually, although we generated 8 in every round trip, because this is actually mixed traffic, up and down. There were very, very few times that we needed 8. To calculate the average, we multiply every parameter by its probability, and we add them up. So that gives us the average number of passengers that needed in every round trip. Let's have a look at some code. So this is actually a real-life run of a PDF calculator. It's going to do 1,000 runs. Incoming up-peak traffic. That's the average number of people that we need in our round trip. So that basically is the number of passengers or number of passengers in the car. And you can see it's settling. It's settling down. You can see some figures are coming up here. So in some cases, really this is saying it's not actually an average, it's a random variable. And we're seeing actually how the random variable changes. And we didn't always need 20, although we generated 20 because we have a basement and a ground floor. We didn't always need 20. And you can see it settling down. So the average value is approaching around 17. Who finds this therapeutic? Raise your hand. Comforting, therapeutic, okay? So to really enjoy this, you have to go to lunchtime. And when you go to lunchtime, so lunchtime is 45%, 45%, 10%. There's a question at the end of this. So lunchtime, 45, 45, 10. What do you notice to start with? The load. Because it's mixed, it's 45%, 45%, 10%. So the average in lunchtime is actually much smaller. The average is approaching 11. I'll shut up and leave you to enjoy that. It's even more enjoyable with the music, isn't it? I'll just let it run for a couple of seconds.
You're answering emails.
What's that?
You answering emails?
Okay, so I'll stop that, go back to something more serious now. So to summarize those two, we have this. And that's the result from these two. You can obviously clearly see the difference between the up-peak traffic and the interflow traffic. So this is really the point of Monte Carlo simulation. We are seeing much more in detail during these 1,000 or maybe a million trials. We see what happens in the round trip time in detail. And I think this was my point to Gina earlier, is that Monte Carlo simulation extends calculation much, much further. And we can now start doing things like mixed traffic. So we can get a round trip time. We can get a car loading and so on. And even we know actually how many passengers were needed in the car under different situations. So what was that music? Sailing by. So this is actually the shipping forecast. It's a short piece of light music. For those who don't know this, you sleep to that?
It comes on at around about 0050 on radio 4.
Are you awake during that time usually?
Awake.
Yes.
The shipping forecast, a variable length comes on, and then we get the national anthem.
Yes.
We move into world services.
Gabriel, you want to say something?
When I hear that, it's the point at which I turn off the radio.
It's what? Sorry, what?
That's the point at which I turn off the radio.
So okay, for people outside the UK, this just comes out of it's a shipping forecast on BBC Radio 4. So we'll quickly talk about accuracy and convergence. So convergence is an important issue with Monte Carlo simulation, and you need to set a criteria for convergence. Convergence means actually we've arrived at a certain value at the end. And this clearly shows that as we increase the number of trials, we're getting a much better convergence with the values. This is just showing an example for round trip time, but it can be used for anything similar. And so that's the running time and then the number of iterations. So you can decide with Monte Carlo simulation how many times you run and what accuracy you're looking for. So to conclude, it's based on repeated sampling with a large number of trials. So you could run 10,000, 100,000, 1 million. We extract the data from every trial, so we know what's happening in every trial, every scenario. And in this case, we looked at it to understand the car loading. You can also use it for things like drive sizing and so on. But I believe it's actually something you can actually extend calculation beyond what it can do. So another useless trivia. Where are the German delegates here? What's this? Any German delegates? Yeah? Anyone else? It's the monument to the Battle of the Nations. Okay, so this is a bit of useless trivia again, but it's just nice to miss. So this is actually a monument to the Battle of the Nations. It's in the city of Leipzig, in the former East Germany. And it was a monument for when Napoleon was defeated there. So they built actually, it was 1813. It took 100 years to build, but it's quite beautiful at night. And when you look at some of the statues, they look like something out of Star Wars. Okay, and thank you much for your attention.